Alright, ladies and gentlemen, so we are going to go ahead and take a look at another video today, but this video is going to be in regards to what are called the Big Five Kinematics equations. So, the reason they're called the Big Five is because these equations represent pretty much everything that we're going to use or do in kinematics when it comes to studying the mathematics behind how objects move. Alright, so there are 5 equations that we're going to introduce, and then what we'll do is we'll talk about how to use the equations in a problem. Now, for the beginning of this, we're just going to, or for the first couple of weeks, we're just going to use these equations by themselves, so one at a time. In the last couple of weeks of this unit, we'll start talking about how to combine these equations together to look at the two-dimensional motion of objects as they travel, let's say, through the air, like a thrown ball. Alright, so first let's take a look at one of the equations. Now, before we go any further, what I'd like to do is introduce some of the variables that we are going to be talking about. And these are all things that students gave little presentations on. So we'll start with delta x. Delta x stands for displacement. And the x means position, and the delta means change. So basically the change in position. And basically what we're talking about is the straight line path from point A to point B. So the shortest straight line path from point A to point B. Then we have final velocity, Vf. We also have something called initial velocity, which would be Vi. And let me get rid of that there so that's out of your way. There we go. Then we have initial velocity, which is called Vi. Final velocity is what it sounds like. It's the ending velocity of an object. Initial velocity is also what it sounds like. It's the starting velocity of an object. Then we have time, which is represented with a t. Now, you're going to notice that one of the variables, and you may not have noticed this, but one of the variables in this equation is missing. So one of the groups talked about acceleration. And you'll see that acceleration is missing from this equation. That means that this equation can be used if we don't know what the acceleration is in a certain problem or situation. So A also stands for acceleration. Alright, here's the next equation. Now this equation can be used to find the displacement of an object if we know final velocity and time, and if we know acceleration. This is what's called a quadratic equation, and you may have recognized that because we have a t squared and also another t by itself. You'll notice that in this equation, initial velocity is missing. So if we don't know what the initial velocity is in a problem, then we can use this equation. Here's the next equation, and you're going to notice that it looks very similar to the first, or the second one that we introduced, except that this one is missing final velocity. Now you're also going to notice that even though these two equations are very similar to each other, one has final velocity in it, one has initial velocity in it, and also the one with the initial velocity has an addition sign. The one that has the final velocity in it has a subtraction sign. And we'll talk about where all these equations came from in another video, but this is really just to introduce these equations. Now, there's also this equation minus the t there. So Vf squared, so final velocity squared, equals initial velocity squared plus 2 times acceleration times displacement. You're going to notice that time is missing from this equation. And last but not least, this is the fifth equation and the most simple one, and you'll notice that this one is actually missing displacement. So this equation could not be used if we wanted to know anything about displacement. So these equations represent what are called the Big Five kinematic equations. Now let's talk about how we would use these in a specific problem. So if you read the problem to yourself, I will also read it aloud. It was once recorded that a Jaguar, which is the car, left skid marks that were 290 meters in length. assuming that the Jaguar skidded to a stop with a constant acceleration of negative 3.90 meters per second squared, determine the speed of the Jaguar before it began to skid. Now the word speed is used here, but we can also use the word velocity if we include a direction. So I'm going to draw a small picture of what's going on in this situation. So before the car skidded to a stop or applied the brakes and decelerated, it was at point A. Now from point A, it began to negatively accelerate, which means it began to slow down until it reached a stop, and we'll call that point B. Now our velocity is going in this direction, which means our acceleration is going in the opposite direction because it is a negative acceleration. And also notice that this matches what's on a Cartesian plane. So since we have a negative acceleration, I'm pointing that acceleration to the left. Now, what else do we know about this problem? We know that the acceleration is a negative 3.9 meters per second squared. So basically what that means is that every second that goes by, my velocity is decreasing by about 4 meters a second. I also know that the distance that it took to go from point A to point B, so its displacement, is going to be 290 meters. And that's also in the right direction. So it skidded to a stop going from left to right. Now it didn't say that in the problem, but I'm just going to assume that to make most of my numbers positive. And also because it gives me the acceleration as a negative number. So we know that the displacement from point A to point B is 290 meters. We also know that the final velocity is 0 meters per second. And we know that because it said it skidded to a stop. And when something comes to a stop, that means it is no longer moving, and that means it has no velocity. So I know that its final velocity was a stopping velocity, which is 0 meters per second. Now, it's the initial velocity that I don't know, and that's what the question is asking. Determine the speed of the Jaguar before it began to skid. So this is what I call my question mark. This is what I'm trying to figure out. Now you're going to notice when you look through here that one of the variables is missing. We know something about initial or final velocity. We know that acceleration is negative 4 meters a second squared. We know that the displacement is 290 meters, and we know that initial velocity is our question mark. But you should also see that time is missing. So what we're going to do is look through all of our equations and find the equation where time is missing, because that's the equation I can use. If an equation has time in it and I don't have any information about time and it's not even a question, it's not even part of the question, then I'm just going to cross that out. So the first equation cannot be used. And let's actually list our variables first. And actually, you guys, this reminds me, this is a good idea to do before any problem. Let's list all of our variables so that they're not in our diagram. So our acceleration is negative 3.9 meters a second per second. Our displacement is 290 meters. Our final velocity is 10 meters a second, and our initial velocity is our question mark. That's what we're trying to find. So again, time is missing. So we have no idea what time is, and it's not even part of the question. So the first equation has time, which means I can't use it. The second equation also has time as a variable, which means I can't use it. The third equation also has time, which means I can't use it. The fourth equation, oops, that's written incorrectly. So the fourth equation does not have time in it, and the fifth equation also has time in it. So it's this fourth equation that I can use because it does not have time in the equation as a variable. So what I'm going to do is work through the problem. First, I'll write out the problem, or write out the equation. Then I'm going to plug in all of the variables with the number to replace them. So final velocity, 0 meters per second squared, equals initial velocity squared, which is my question mark. So I'm going to keep that in there, plus 2 times acceleration, and also times displacement. All right, so 0 squared is just 0, so that's easy. I don't know what my initial velocity is, but that's what I'm trying to find out. And I'm going to multiply all this together. I'll do everything that's in the parentheses first. I'll multiply the parentheses with each other, and that comes out to negative 1,131 meters squared times seconds over seconds squared. Now, how did I get that? Well, it's a meter times a meter on top, and then seconds squared on the bottom. And that'll work out in a little bit. All right, so now I'm going to rewrite this, and 0 equals vi squared plus, or minus, and I'll multiply 2 times what's in parentheses. So 2 times a negative turns into a negative, so minus 2,262 meters squared times over seconds squared. Okay, so since I want to figure out what initial velocity is, I'm going to move my 2,262 from one side to the other of that equal sign. So this is what's called isolating the variable. So I'm going to do that by adding 2,262 meters squared over seconds squared to both sides of the equal sign. And I can cross that out now on one side because those two cancel out, and I end up with positive 2,262 meters squared over seconds squared, which equals initial velocity squared. Now, I'm going to go ahead and, since I need to know what initial velocity is, I'm going to find the square root, similar to what we were doing in the previous lesson with our Pythagorean theorem. So, find the square root, boom, boom, and using my calculator, I can solve that initial velocity is going to be the square root of 2,262, which comes out to be, oh, and notice that our squared all disappear because the square root is an opposite of a square. So the square root of 2,262 comes out to be 47.6 meters per second. And that is my initial velocity. So the car, before it began skidding to a stop, with a negative acceleration of 3.9 meters per second squared, was traveling 47.6 meters per second. Now some of you may be saying, okay, is that fast? Is it slow? It sounds fast, but how fast is that? So let's go ahead and solve for what that is in the English system. So 47.6 meters per second. I'm going to rewrite this, and that equals how many miles per hour. So going from what the group was telling us who worked on speed and velocity, 47.6 meters per second can be multiplied with 1,609 meters on the bottom, and that is equivalent to 1 mile. Now you're going to notice that meters on top cancel out meters on the bottom, and I'm left with 47.6 miles every 1,609 seconds, because I'm just multiplying across. So 47.6 times 1, and then 1 second times 1,609. All right, now I can take that and get rid of my seconds by multiplying by 3,600 seconds on top and 1 hour on the bottom, because those two equal each other. They're equivalent to each other. Seconds cancel out, and I'm left with, on top, multiplying across, 171,360 miles over 1,609 hours. Now, since I don't want all of that, I just want something that's miles per 1 hour, I'm going to divide, and this leaves me with 106.5 miles per hour. So the car was traveling 106.5 miles per hour before it applied its brakes to come to a stop and skid 290 meters. So what we just did here was we not only figured out what our final answer is in miles per hour, but we also solved for, using one of the big 5 equations, the initial velocity in this problem. So the initial velocity before the car began to slow down and skid to a stop. The idea behind this video, you guys, is to introduce the big five equations, which are on the left-hand side here, but to also show you that there's a method for solving these problems, which is, let's try to diagram what's going on. Let's fill out all of our variables, figure out what our question mark is, figure out what we have no idea about whatsoever, and then decide which equation to use from there. Okay? And then from there, it's just kind of plugging in numbers instead of letters and solving for that unknown variable. All right, we'll go ahead and practice this stuff tomorrow, and then we'll have a video at some point which will explain how did we get these big five equations to begin with.